Hello everyone, and welcome to Insider Sample Prep Strategies for Faster, More Accurate Readings. I'm Wendy Ortman, an Aqualab Customer Support Expert and Application Scientist in the Food Science Department here at Meter Food, formerly Decagon Devices. In case you are not aware, I'd like to let you know that we are changing our company name from Decagon to Meter, effective in January 1st of 2017. The group that will serve food quality customers is going to be known as Meter Food. We're making this change to focus on building the quality assurance lab of the future and decided that Decagon and Aqualab weren't the right names for this. As we make the change, you'll probably see both Meter and Decagon names be used, but we will continue to offer the same products and services you currently buy from us, including all Aqualab water activity meters. We're excited to show you what we're building here at Meter, so if you want to check out our progress, you can go to meterfood.com and see what we're doing. Today the presentation will be about 45 minutes, followed by approximately 15 minutes of Q&A with myself. First, a couple of housekeeping items. We do want this to be interactive, so we encourage you to type any and all questions in the questions pane. We'll be keeping track of these for the Q&A session at the end. Second, if you're wanting us to go back and repeat something you may have missed, no problem. We're recording this webinar, and we'll send you out a recording via email within the next 3 to 5 business days, so you'll have a copy. All right, let's get started. So today I'm going to be talking about 4 main topics with regard to sample preparation to help you achieve faster and more accurate readings. These 4 topics are temperature, sample exposure to the environment and how to minimize that, some special sample types that require additional time or methods, and lastly, sample preparation techniques for a variety of different materials with some examples on how to approach that and how to optimize your own sample preparation. So the first topic is going to be temperature and water activity. Temperature plays a critical role in water activity testing and is a variable that must be accounted for when trying to achieve accurate and consistent results. Products are tested for water activity in all stages of production, and the range of temperatures for incoming samples can be substantial. So whether you're pulling samples straight out of an oven to take readings to monitor your process, or whether you're pulling samples that have already been packaged and cooled down or at room temperature conditions, you do need to monitor the temperature of the reading conditions. One of the common issues that help troubleshoot is how to pull samples from a production line that are still warm and get quick readings for feedback on the process. So I'll offer some tips on how to approach that. We're also going to talk about the importance of temperature and water activity readings just in general for research purposes and how to better understand your product. So to discuss this, we need to talk about the water activity measurement itself. So water activity is a measurement based on thermodynamic principles, and if you look at the equation for water activity on your screen here, you can see that temperature is integrated into how we calculate water activity. These measurements are temperature sensitive, and as water activity will change with temperature, you do need to monitor temperature as a critical variable. Therefore, taking readings at defined temperatures and maintaining temperature throughout the reading is crucial for getting consistent and accurate results. So I just mentioned that water activity is temperature dependent. So if water activity is going to change with temperature, it is necessary to control temperature. Different water activity systems will have different approaches, and you'll either need to compensate for the temperature difference between the sample and the sensor, or wait extended periods of time to ensure thermal equilibrium. If you have a sample that comes in warm and you put that into a cool chamber, you should wait until the sample temperature is at the chamber temperature before taking a reading. If you do not, the water activity will be changing as the sample comes to thermal equilibrium with the chamber, and you'll either get extended read times or you'll actually get inaccurate read times if the sample is basically changing slow enough that it kicks out a reading. So this schematic is basically looking at that thermal equilibrium. So if there's any differential between your sample temperature and your read chamber, you do need to wait until you get equilibrium for that water activity value to stabilize. In some systems, such as the Aqualab Series 4 instruments, the system itself controls the read chamber and will also account for differences between the sample temperature and the sensor temperature. For other models, older models out there, temperature is not controlled, so you do need to wait for thermal equilibrium before starting a reading. So for consistent and accurate results, a temperature-controlled instrument is highly recommended. Some additional reasons to monitor temperature. So aside from taking the actual reading, temperature is important for research purposes and understanding a product's behavior and potential shelf life. One common study to perform is looking at temperature versus water activity and determining how significant the change in water activity is as the sample is exposed to different temperature conditions. As I mentioned, the Series 4 instruments have the ability to control the sample chamber, and this can be done anywhere from 15 degrees Celsius to 50 degrees Celsius for this very purpose. So you could set the chamber to a specific temperature and monitor how your sample performs at that given temperature. These numbers can be useful when looking at accelerated shelf life testing, which is typically done at elevated temperatures. Another aspect of that is looking at isotherms. These are a way to capture how the sample behaves at varying water activity conditions. The example below shows a sample of drinking chocolate powder at 3 different temperatures. In this example, the sample has a critical water activity which is indicated by the red circles. Beyond this water activity, this particular sample is going to undergo a physical change. And you can see that that critical value at which that happens is very different between 25 degrees Celsius and 40 degrees Celsius. So you can see that temperature is going to play a critical role in your water activity measurements. This also becomes an important variable if you're doing lab-to-lab comparisons or even comparisons within the same facility but during different seasons of the year. If your instrument does not control the temperature at the time of taking the reading, you can see fluctuations based on location or time of year, as ambient temperature can fluctuate quite a bit based on the conditions in the lab environment. This can have a significant impact on your water activity readings. Therefore, controlling the temperature using a temperature-controlled instrument will help eliminate this problem. You can also use temperature trays to bring all of the samples to the same standard temperature prior to taking a reading. The standard temperature for routine quality assurance testing is typically 25 degrees Celsius, but some regulations will specify a particular temperature for that type of product. The AOAC method calls for a standard temperature of 25 degrees Celsius, but you'll also find some European regulations call for 20 degrees Celsius. So be sure to know what temperature is required for your product before you assign a temperature to all of your readings. So in looking at sample temperature, one of the most common questions we receive in our support department is how to deal with samples that are at a different temperature than the standard 25 degrees Celsius. So I mentioned earlier, many samples are going to come in from production with elevated temperatures, whether that's coming out of a drying system, baking process, extrusion process. So there are a couple different options for dealing with this scenario. One is to increase the temperature of the instrument if you have the capability to do that, so that the temperature of the chamber more closely matches the temperature of your product. This is going to help reduce cooling time, so this is ideal for in-process measurements that are used to make feedback decisions. So for example, if you're pulling products out of a dryer and they're quite warm, if you can read at that elevated temperature, you get a much quicker reading, which would allow you to make decisions such as the product needs to stay in the dryer longer or whether or not it can be released and finished processing. If you do this, however, you'll have to go through some additional steps to establish the relationship between temperature and water activity for that product. So if you're reading at 40 degrees Celsius to match the product temperature coming out of a process, know that the water activity at 40 degrees Celsius may not be the same as the water activity of that same product at 25 degrees Celsius. And this relationship between temperature and water activity is product specific, so that must be determined. You can do this by monitoring your product at a series of different temperatures and see how much that particular product is going to change. Once you do that, you can read at those elevated temperatures, and then you know approximately what your water activity would be at 25 degrees Celsius. The other option is simply to allow the sample to cool until it's within a few degrees of the desired temperature. So this method is going to work best if you're not reliant upon quick readings to make quick feedback decisions in process. Most of our instruments are set at the sample temperature needs to be within 4 degrees of the desired measurement temperature before the instrument will start taking a reading. You can make this more stringent. Generally, the closer matched they are, the better, more accurate results you're going to get. The care that needs to be taken with cooling samples, however, is to cool them slowly enough to prevent a lot of condensation buildup, but still protect the sample from environmental conditions. So a lot of people have the tendency to just pull a sample and leave it exposed to the environment as it cools down so you don't get condensation. But if your product's susceptible to rapid changes with exposure, then you have another set of problems that you have to work with. Anyone who's worked with a Series 4 instrument knows that if you put a sample in that's warmer than the read chamber, the instrument will beep at you and tell you, remove the sample, it's too hot. The reason for that is if you put a warm sample in a cooler chamber, you'll get water condensation on the chamber surfaces and the sensor surfaces, which will impact your measurement. So in that case, it's better to pull your samples, have them in some type of mostly sealed system, especially if it's a sensitive sample. Allow it to cool slowly before actually taking a reading. One thing that is very beneficial is to use something like a temperature tray. Set your sample on that. It's going to help it cool down and come to the same temperature as what your instrument's set at. For cooler samples, these are a little bit easier. You don't have to worry about condensation. You can simply put them in the chamber and start a reading, although as that sample equilibrates with the temperature of the chamber, its water activity will continually change. So if you put a cold sample in, one of the things you're going to see is extended read times. If you put that sample on a temperature tray and warm it up first, you'll notice much shorter read times, but you do have to allow that sample to come to equilibrium with the temperature that you're going to be reading it at. So if you're pulling hot samples, do take a little bit of time to decide, at what point are you taking the reading, how important is that reading to be incredibly accurate, and then take the steps to try and get that sample to the appropriate temperature before taking your reading, and you'll end up with more consistent results that way. All right, so the next topic I'm going to discuss is sample exposure to the environment. I did allude to this a little bit in terms of if you're pulling samples out of process and having to allow them to cool, you do want to protect that sample from exposure to ambient conditions. So this is one variable that often doesn't get recognized as a contributing factor to variable results in water activity testing. And so any sample is going to equilibrate with its surroundings. So if you leave a sample open in a container that's not sealed before testing, it'll always begin to equilibrate with the conditions in that room. And so water migration can happen within a product. So if you look at the schematic here, we've got component A and component B. So you can think of this as a cookie with a filling. If the component A and component B are at different water activities, you'll get water movement between those. So it's basics of water migration, that the energy of water dictates how water moves. But the same concept applies to water movement between your sample and the environment. So if it's more humid in the room than the water activity of the sample, you're going to get water movement from the environment into your sample. Same applies if you have a sample that's a high water activity, but you're dealing with low water activity conditions in the lab. That material is going to start to lose water to the environment. So you do have to make sure that you prevent that change prior to reading. So this can be prevented with proper sealed containers for the short term, and for long term and final product, that's basically the purpose of your packaging, is to serve as that barrier between the product and the outside conditions. So in terms of sample exposure, I often get asked about how important this is, and will a sample really change that quickly? The answer is definitely yes, and it's incredibly important in some cases because the sample can change quite rapidly. The example on the screen is a dried powder blend. So on the left you can see the sample is a nice fine dry powder. So this is under controlled low humidity conditions. On the right is what the same sample looked like after only 10 minutes of exposure at 40% relative humidity in the lab. So you can see that the sample physically changed and that it caked and clumped up. So this was less than 10 minutes. So if you're trying to monitor your product in process, you need to make sure that as you pull that sample, it's immediately going into some type of sealed container, and that you're testing that immediately in the instrument. So if you were to pull this sample and just leave it open in a sample cup like this, you can see that that material is rapidly absorbing water from the environment, and therefore its water activity is going to change substantially. So it's definitely important to maintain sample integrity prior to testing. Even short periods of time can result in significant changes. So this is very product dependent. Some material is going to change drastically in a short amount of time. Some material might take a few hours or even days to really adjust. But general rule of thumb, keep your samples in a sealed container and test as soon as possible. So this effect I mentioned is often sample dependent, but will also depend on the conditions in the testing environment, and how your sample preparation method feeds into that can be another variable. So this example here is looking at dry kibble. So if we were to grind the sample to the image on the left and leave it on our bench for 5 minutes before taking a reading, would we see a difference in that water activity value? So I've actually tested this with customers, and yes, as soon as you grind the sample, you've maximized the surface area and accelerated water gain or loss for that material. So if we were to take a reading immediately, we'd see a slightly different water activity value than if we'd let that sample sit out for about 5 minutes. And that change is really going to be dependent upon the humidity conditions in your lab at the time of testing. Now if we take the same product, but we leave it in whole kibble form, we don't see nearly as much of a change after short exposure times. So the take-home point for this is that changes in your sample preparation method might make your product more or less susceptible to changes in the environment. So in either case, the sample should be kept in a sealed container until the time of testing, but you might have a little bit more leeway depending on how you're preparing that sample. All right, so preserving a sample. I keep talking about making sure that you keep your samples in a sealed container prior to testing. So we've got some examples on the screen here of ways that people collect samples and maintain samples. If your sample is being transported for a very short period of time, so something straight from the production line into the QC lab where it's going to be tested immediately, something like a Whirlpack bag might be acceptable. For anything longer than, maybe a 30-minute time frame for storage, however, a Whirlpack bag really isn't a very good barrier. So if the sample is going to be shipped to another lab or facility, if it's going to be stored for any length of time, you will need to ensure that the product doesn't change over time due to exposure, so you're going to need a better sealed container. So containers like glass jars, specimen cups work really well. They work even better if you're parafilming those for long-term storage. Probably one of the best things for long-term storage is to use something like a foil pouch that's sealed. This is basically going to serve as one of the best barriers for your product. Also, if you have material like freeze-dried components, extremely hygroscopic compounds, you'll need a much more effective barrier than if you're working with something like a pet food or a cured meat, simply because those samples are going to be so much more susceptible to the environmental conditions that they're going to change much more rapidly. So you'll need to get those into a suitable barrier basically immediately and then test almost immediately. So based on what you're doing, if you're going to be testing right away, or if you need to ship samples, maybe you have a centralized location for your company, or if you're doing any third-party testing at a test lab, make sure you're sending samples in an effective sealed container. Otherwise, you'll likely see some pretty significant changes in what you would get at your facility versus what you've sent out for additional testing. All right, we're going to move on to the third key element, which is looking at special samples. So these are sample types that require special considerations. For these samples, you need to know what water activity value you're looking for, what read mode or sensor will be appropriate for that product type, and in some cases, how to actually prepare that sample. So for special samples, what do we mean by that? So primarily this is in reference to types of material that either need specific sample preparation methods or need a certain type of sensor to read that product. So I'll cover some main examples of material that's slow to equilibrate, what to expect when reading those products, go over, these are kind of main examples. You're going to find variability within each of these categories that might require its own tweaking, but this should at least give you an idea of kind of where to start. So some of these examples, we have coated samples, so any material that's got some type of coating surrounding it. Emulsions, so the emulsions you can have either water and oil, or oil and water emulsions. Glassy samples, these are typically going to be things like your hard candies or cough drops. And then volatile material, and I'll talk a little bit more about what we mean by volatiles. If we take each of these individual cases, the first one I want to talk about is coated samples. So this is any type of material where you're going to have essentially two different components, so it is a multi-component product, one component being your coating, and then whatever's in the interior. So a couple examples I put up here, we've got gel-filled capsules, chocolate-covered pretzels. So in both of these cases, you do have a distinct coating material. So in terms of what water activity do you want to understand, this is going to come down to, do you want to know the water activity of the coating, or do you want to know the water activity of the interior? So that coating is going to serve as a protective barrier to ambient conditions, but it also is a barrier for water escaping out of the interior into the vapor phase where we can read it. So if you simply want to know the water activity of the coating or the exterior of the product, you'd read that product whole and intact if possible. However, if you actually want the water activity of the mixture, especially what's on the interior, then you'll need to go through some sample preparation methods that break that open and expose the interior so you can get readings that way. So you will have to tweak sample prep with these methods or with these type of products in order to achieve optimal readings. Another one that can be a little bit tricky are emulsions. So emulsions such as cream, which is a water or an oil and water, or butter, which is a water and oil emulsion, contain lipids that act as a barrier to vapor diffusion. And what that really means is that you have prolonged read times. So these type of samples are going to take a lot longer to get an equilibrated reading. So anyone who's worked with these, you've probably experienced, maybe you're reading your salt solutions 5 minutes, you've read some other products, they typically read in about 5 minutes, and then you read an emulsion and it takes 15 or 20 minutes. So the first thing is that's normal. That's to be expected for these product types. They simply take a lot longer to equilibrate than other material. So a couple considerations for these. Depending on the type of instrument you're using, multiple readings should be utilized to ensure that equilibrium has occurred. Within the Series 4 instruments for the Aqualab, there are a couple read modes that can help with this. So we use continuous mode, which basically allows the sample to just continue taking single reads, and you can plot that out and see when the sample is actually truly stabilized. There's also a custom mode option, which allows you to select a desired number of readings within a certain value. It's another kind of secondary way to check and make sure that the sample has finally stopped changing. The reason for these additional read modes is that the samples can sometimes change so slowly that it tricks the instrument into thinking that that sample is actually equilibrated when it really truly hasn't. So one trick with these sample types that might cut down on equilibration time is to mix them with glass beads. So this increases the surface area of the sample and can help reduce those equilibration times a little bit. So if you are working with a lot of emulsions, mixing that sample with glass beads might be something that you can try to reduce read time. The next sample that requires special considerations are glassy materials. So the most common example of these are going to be things like hard candies. So with glassy compounds, due to the physical state of the material, they do not absorb water very well from the environment and can take a very long time to read. So sample preparation methods are another case where these can be useful in reducing read times. So if you try and run a whole intact piece of hard candy, you're going to see very long read times, and that's basically because that sample is having a tough time equilibrating. Water doesn't move through that matrix very effectively. So if you take that hard candy and crush it apart into some pieces, again, this is increasing your surface area, so that's going to help reduce those equilibration times because you're exposing more of the product. For these type of samples, testing should be done immediately, so you don't want to allow these samples to be exposed for extended periods of time. Excuse me, especially not after you've crushed those. So once you've taken a hard candy and started to crush it and break it open, you definitely want to read as quickly as possible. So next, slow water emitting samples. So this actually encompasses a couple of the examples I've already talked about. It would also be true for any material that's very high fat content. So if you're measuring oils, any of the emulsions, glassy material, basically any matrix where you're having a tough time getting water molecules to move through that substance. So some extremely dry and dehydrated material, very viscous material, high fat, glassy compositions, all of these are going to require multiple tests due to the slow water emitting properties. And that's simply because the change in water activity is so slow that the instrument determines that test to be complete, even though changes in water activity are still occurring. So it's a lot like what we talked about with the emulsions. So you can use continuous and custom mode to make sure that you're getting true equilibrated values. That's one option. You can simply take consecutive readings if you have other types of equipment. And you can do some things with sample preparation methods, like mixing with glass beads or trying to break that material open to try and improve your equilibration times. But for the most part, for these sample types, you just have to be aware that they are going to take a lot longer to read than what you might be used to. All right, the next topic is looking at, in particular, the dew point method and volatile material. So when we talk about volatile material, we're generally speaking about small volatile compounds, and the ones that we know have an impact are compounds that have both polar and nonpolar carbons. So you can see some examples here on the right. So we do see interference with the Childner dew point method with samples that contain propylene glycol, ethanol, and propanol. So these are three of the most common ingredients that we know have a significant impact on the Childner dew point method for water activity. Another one that we know to be problematic is acetic acid. So we actually went through and did a lot of work in trying to identify which compounds were creating issues for this method and what was the common theme. Again, the common theme here is that there's small compounds that have both polar and nonpolar carbons. So we don't see interference with glycerin. And if you look at the structure of glycerin, that's because all of those carbons are polar. So it doesn't meet the criteria. But the rest of these we know to have a significant impact on dew point readings, and they typically are going to cause your readings to be higher than what the value actually is. This interference is likely due to a surfactancy effect on the mirror surface. So if you know that you have ingredients that are on this list, if you're working with final product, where these might be an ingredient in the mixture, in terms of ethanol, anytime you're dealing with addition of flavorings, there's usually a fair amount of ethanol carried over in the flavor compounds that you'd want to keep an eye on. If you do have these ingredients, there are a few solutions to ensure that you're getting accurate readings. So one that's been around for quite some time is the use of a capacitance, or we call it sometimes a volatile sensor. So with these sensors, they're less sensitive to volatiles. However, they're a less accurate sensor than the Childner dew point method, which is unfortunate, and they also are prone to hysteresis and constant recalibration issues. And for a lot of capacitance sensors, even those over time can be poisoned by some of these volatile compounds. So they will read it much more effectively than the chilled mirror, but it doesn't necessarily mean they're completely impervious to those substances. So one of the newer options in order to deal with these compounds is the use of a system that uses a tunable diode laser. So we have an instrument that utilizes this. So this laser can be controlled to a very specific wavelength with a response at 1854 nanometers, which is limited to just water. And so this sensor is basically not impacted by any volatiles. It can run pure alcohol, gasoline, without any significant impact. So one of the things I would like to bring up is if you know that you have some of these compounds and you're using a Childner method, if you're seeing results that seem a little higher than they should be, then it's likely that you're seeing an impact on that sensor. So if you know you have these type of ingredients or they're common, you might want to look at a different sensor type to read those to ensure that you're getting accurate readings. All right, we're going to move into the last area, which arguably I think is the most interesting, which is sample preparation methods. This is one of my favorite things to work on. I spend a lot of time in customer sites, kind of help optimize sample preparation methods for different product types. So what I'm going to do here is give you kind of some key concepts, some generalized ideas of how to approach sample prep, and then I'll go through a bunch of different specific examples that hopefully You'll get some ideas of how to approach your own product based off of this. So for sample preparation, some main guides to keep in mind. So the first thing is knowing that water activity is an intensive property. So it's a bulk property, meaning that we don't need to work with a defined amount of sample. So it's not like a moisture content where you have to weigh out a specific amount of material before taking a reading. So the key here is that you want to get a representative sample, and you need to have enough sample in your sample cup to equilibrate the water in the product with the vapor phase. But aside from that, you're not limited to working with a specific weight of material. In terms of volume, if you're familiar with our sample cups, generally we say fill your sample cup half full. That ensures that you're covering the bottom surface of the cup so that your sensor is taking sample temperature correctly. The reason we say don't fill it full is that it's pretty easy, slip of the hand, to spill some sample into your chamber if your sample cup's very full. So that's more of a cleanliness factor in reducing contamination. But otherwise, as long as you've got some material in the sample cup and you're covering the bulk of the bottom, you have enough material in most cases. In terms of sample types, the range of test material that you can run in an instrument for water activity can range anywhere from raw ingredients to finished product. You can read liquids, you can read powders, you can read gels. There's really no limitation as long as you can fit those products into the sample cup. And so depending on what you're testing, a couple key considerations are that you do need a representative sample. So if you're dealing with a fairly homogeneous mixture, if you're reading flour, it's very easy to get a representative sample. If you're running a multi-component mixture, so something like a trail mix, you need to make sure that the sample you're pulling and reading water activity has a representative amount of each of those ingredients. So you do want to make sure that you're getting the correct ratio of ingredients in your sample cup as what you'd see in the finished product. And then lastly, if you're doing any slicing, grinding, crushing, chopping, whatever it may be, make sure that process is consistent. This is probably the biggest mistake I see is incorrect sample preparation methods for product type. So once you've optimized which type is best, you need to stick with that and make sure that everyone is prepping that sample consistently. All right, so one of the key things prior to actually getting into preparation methods themselves is sample prep cleanliness. So before you start preparing your samples, make sure your prep surface is as clean as possible. I know a lot of instruments are out on production floors. People usually kind of laugh at me and say, how clean does this really have to be? Basically, just the area where you're setting down your sample cup and the reed chamber of the instrument need to be clean. If the outside of your sample cup has a bunch of residue on it, and you put that especially into a Series 4 model where the entire cup is inside the chamber, then you're just bringing in contaminants and contaminating your chamber. So just try and make sure the surface is wiped off. You don't have a bunch of crumbs or grease there while you're preparing your sample. The other thing, use disposable sample cups that are clean. So we provide disposable sample cups. That's actually recommended in most of the approved methods like ISO or AOAC, simply because if you're reusing sample cups, you're bringing in contaminants from previous readings. So you really need to make sure that that sample cup is clean, it hasn't been used. They are disposable, so it's easier to just get a completely new one. If you are reusing those, make sure they're washed and dried properly before putting another sample in there. And then make sure that the sample chamber is clean. So that seems pretty straightforward and obvious. Cleaning is probably the biggest battle that a lot of people face. There's going to be the obvious contaminants, crumbs sitting in the chamber, things that you can actually see, but making sure that the chamber is cleaned properly on a regular basis, even for contaminants that you can't see, is crucial to getting correct readings. So sample cleaning is a whole other topic. I really won't go into that in detail. So we'll move on to looking at sample prep, but keep in mind that cleanliness is going to be kind of your first step. All right, so the first category of products I want to talk about are multi-component products. So this covers a huge range of products. Basically what we mean is you have separate individual components in that mixture. So these are going to be your non-homogeneous substances. So the example up here is a variety of different bars. So we've got kind of granola bar types, some protein bar-looking substances, different fillings. Some have pieces of nuts in them, some have pieces of fruit, some of them are coated. So with products like this, one of the questions I always get asked is, how do I ensure I'm getting a representative sample, and what's the best way to sample this product? So you can see here we've got 4 very different types of bars, and I have in the sample cup basically a representative sample of how I would approach taking a reading on that material. So on the left we have kind of more of a granola bar, so we've got some oat material. There is some like a white chocolate type coating on there, a yogurt coating, we have pieces of fruit, we have pieces of nuts. So for this particular bar type, and one of the things with bars or similar products is you want to cut out a sample towards the middle. You don't want to cut off the very end. One is if it's got a coating, then that's not necessarily a representative sample. But the interior of most products is generally going to be your higher water activity. So if you're doing this especially for microbial stability, pull a sample more towards the interior, because that's going to be more accurate for the overall product. So for the granola bar, basically took a cross-section slice out of that and then broke it apart a little bit, since we've got some nuts and some fruit in there. Kind of pulling that apart is a more optimal sample. So you can see we've got some pieces of oats, there's a piece of fruit in there, there's a piece of nut. We've got some of that, coating material included in that sample. For the next bar over, this is kind of a protein bar, so it's got a chocolate coating. So this one's a little bit easier, and you simply just take one single cross-section slice and lay that in the bottom of the cup. In a lot of my examples here, you're going to see that there are gaps in the bottom of the cup, that we're not covering the entire bottom surface. That's actually fine. You want to try and make sure you're covering as much as possible, especially towards the center of the cup, because that's where our infrared sensor is taking sample temperature. But you can have gaps between things. That's completely acceptable. In some of my examples, there's probably not going to be enough sample in there to be optimal, but it made the picture better so you could actually see what the pieces look like. So general guide, try and make sure at least the center of the cup is covered, but you can have those gaps. So the third bar over, you can see this one's got, looks like slivers of almonds and some chocolate coating on top, and then we've got some kind of granola cereal type substance in the middle. So the same thing on this one, I simply took a center cross section and then broke that apart a little bit, since this one also had pretty thick consistency. There's a kind of a sticky binder to help you pull that apart and maximize surface area. Will help speed up the read time. And then the last one is also a pretty simple one. Simply took, since this was a very thin bar, I took 2 cross-section slices and laid those in the cup. And so that's going to allow you to get more product in there, more surface area. So hopefully this gives you a little bit of an idea of kind of where we're going with these multi-component products, just making sure you're getting something representative with the correct ratio. So for things like this, where you can just take a cross section, that works great. All right, so another example here is a cereal bar. So this is very similar to the first example. This is some work we did in the lab kind of showing the timeline of how to prepare the sample. So again, we're going to cut more towards the interior. We're going to take that single slice and then chop it into smaller pieces. The reason we do that for this one is that the filling in the center, as you maximize surface area, that's going to help speed up your read time. So we've chopped it into even smaller pieces. We're not doing any grinding here, just simple chops with a knife and then placing that in a sample cup. So for something like a cereal bar, this is going to be pretty optimal. This is how you would want to approach your sample preparation. Moving towards another multi-component product, so this is a dried fruit mix. So if you've got any type of like trail mixes, dried fruit mixes, cereal with fruit chunks in it, you can kind of think of anything along this line with different dried components being mixed together. So for dried fruit in particular, a lot of times as it goes through a process, a bit of a coating is applied to the outside, especially if you've got like whole berries. Sometimes they'll do an oil coating on the surface. Again, with the idea of trying to maximize surface area, but without creating a lot of damage to the sample. So that we'll get into that a little bit more later. But you don't want to grind the sample to a fine paste or a fine powder, because then you're actually altering the physical state of the material, That's not your finished product, so you don't want to basically prepare the sample to that extent. So in this case, we're going to take those fruit pieces, and just to speed up read time, we're just going to do one simple slice through those, and that's going to open up the interior, and if there was something like an oil coating, we bypass that. So you're going to take your chopped pieces, place those in the sample cup. Again, looking at the overall mixture of the blend, we try and get about the same ratio of, in this case, it looks something like maybe cranberry pieces with whatever those yellow ones are, might be mango or something, to get the correct ratio of those in the sample cup. Things like fruit pieces, meat, anytime you're dealing with tissue, structure, or plant-based materials where you've got cell wall structures to deal with, the rule of thumb is try and do minimal sample prep possible. So in this case, we want to chop it up because we need to expose more of the interior of these and maximize the surface area a little bit to speed up read times. But you don't want to go through a grinding process. If you start grinding, you're actually breaking down tissue structure, breaking down cell walls, even maceration of the tissue. And that's also going to introduce heat into the product, which will sometimes accelerate water loss. Adding heat can also alter the water activity if you're reading that right away. And also, it would be no longer representative of your finished product. So in this case, if we took the dried fruit chunks, placed them in a food processor, and basically blended that into a paste and then read that, that's no longer representative of the product that we actually have in the bag. So you want to try and keep the product as close to its final form as possible, but then making sure that you're preparing it in a way that's optimal for readings and for read times. All right, so we talked a little bit about coated examples earlier, and that those require some special considerations. Talk a little bit about how to prepare those samples. So we've got two examples on here, and really the key with coated material is, do I want to run those intact or sliced open? So I mentioned before, if you run these things whole and intact, you're primarily just reading whatever the surface is, which is usually going to be very close to your ambient conditions. So in the case of our gel capsules, if we prepare a sample cup and run those whole, we're basically just looking at whatever the surface water is on the outside of that capsule material. Now if we take those and we do one cut open and then pour that mixture inside the sample cup, so now you're going to have broken apart capsule material as well as whatever that film was. So this is going to be optimal for looking at the water activity of the entire product, making sure you're capturing what the interior is reading, which is usually going to be the area of concern. Next example is looking at chocolate-covered raisins. So in this case, if we run those whole, we're primarily just looking at the surface of that chocolate coating. Now if we slice those in half and just one slice is sufficient, you can now see in that middle picture that we've captured the chocolate coating, but now we've exposed the interior so we can actually read that raisin. So you would cut a bunch of those in half, place them in your sample cup. In this case, you probably want a few more pieces in that sample cup to cover more of the bottom area, but that's how you'd want to read it if you're trying to get a reading of the entire chocolate-covered raisin, including the interior. Glassy samples, this was another one of those special considerations. So again, we want to look at whole versus crushed. So if you place this whole candy into a sample cup and read it, you're probably looking at, I'd say, almost minimal 15 to 20 minute read time on that product. But if we take that and just put it in something like a mortar and pestle and just break it apart a little bit, I've seen people use hammers, and then you just collect some of those shards and put those into a sample cup. You've maximized the surface area a little bit. You're really not changing the structure too much. You're not going through excessive grinding, not turning that into a powder. So it will reduce your read time and allow you to get a better idea of what the water activity of that sample is. So with glassy samples, breaking those apart a little bit is optimal. So then moving into some other examples. So this is going to be focused not so much on that the sample itself requires special considerations in order to prepare it. So like a coated sample does, because you do need to know what water activity value is in the interior, which will require some special preparation methods. But in the case of just trying to optimize and get fast and repeatable results, there are a few things to consider as well. And so optimizing sample prep is usually one of those. So again, the rule of thumb here is increasing the surface area with minimal damage to the sample. Another option here for fast and repeatable results that I wanted to mention is the use of a new read mode that we offer in the Series 4 instruments, which is called low emitting mode. So this is where you can actually choose what accuracy you want on your reading. So you can decrease the accuracy a little bit to achieve faster read times. So we have people who do need to read in process right out on the production line and use that reading to feed back into the system and say, no, we need to dry this sample longer, we need to cook longer. So in that case, time really is of the essence. So the faster you can get a read time, the better. So, the normal 003 accuracy is needed for quality assurance, but when you're monitoring in process, accuracy of 0.01 might be sufficient to make the call. Then you can use low emitting mode, adjust the accuracy that you desire, and get a faster read time. So it might not be fully equilibrated value, but you'll at least have a rough idea of what the product's at. So that is an option if you wanted to go that route. All right, so looking at a couple examples of material and optimizing sample prep for not only speed of readings, but also repeatability of those readings. So one area that I work a lot with is pet food. And so within pet food, there's been kind of the long-standing habit of grinding the sample. And really that's been carried over from the use of moisture content data. So a lot of moisture content methods do require that you grind the sample to a powder. Thinking of water activity, I really want to encourage people to kind of leave that mentality behind and think about it in terms of some of the items we've discussed. So if you have a whole piece of kibble, put that in the sample cup and you take a reading. It is going to be the final form of the product, which is ideal. But a lot of pet food sometimes has a little bit of an oil coating on the surface or some type of coating that they use as a little bit of a protective barrier. In doing that, and along with the matrix of kind of that compacted extruded material, if you run those pieces whole, you will see extended read time. So it's pretty typical, I'd say, on a dry kibble to see read times of 10 to 15 minutes, sometimes longer. So for the purpose of speeding up read times, you can break those apart into smaller chunks. So if you look on the far right side, we just used a mortar and pestle, threw about 5 pieces of kibble in there, just broke it apart. You can see, those size of pieces, even a little bit bigger, would be sufficient. What this does is it breaks that apart. We increase the surface area a little bit. We expose the center pieces of those kibble. And this is going to allow you to generally drop the read time by anywhere from 5 to probably 7 minutes on average from running it as just whole pieces. So pretty much the same value, but about a 5-minute reduction in read time per sample can be huge for some customers. So that would be your optimal method. Now in the center we have the method that I see a lot of people do, which is take that product, put it in like a processor or a grinder, grind that to a fine powder. So again, going back to the idea of trying to do minimal damage to the sample, when you do this with pet food, you're basically breaking apart some tissue structure. You've maximized the surface area to the point where you see very rapid water gain or loss with the environment. You're introducing heat in that grinding process, and now you've got a powder which doesn't really resemble your final product at all. So what I've seen with a lot of customers is if you take a sample and you just crush it, even if that sample is exposed for short periods of time, you get much more repeatable results. Whereas if you grind that dry kibble, you're going to see a lot more variability, and it's going to be hard to get consistent readings because every time you grind it, based on the conditions in the lab, you're going to see a lot more rapid change in that material due to exposure. So for repeatable results, definitely using the crush method is optimal, as well as for read time. Another example here is looking at almonds. So pretty much going to be the exact same idea as our dry kibble. Almonds, a lot of nuts kind of have their own protective barrier if you read them whole and intact. So if you're running a whole nut, you're going to see a lot longer read times. versus if you take those and just break it apart, expose the interior. So like the dry kibble, with almonds, what we saw was whole almonds are taking anywhere from 15 to 20 minutes per reading, whereas if you broke those apart and crushed it, it usually drops that down to maybe 5 to 7 minutes per reading. So substantial savings in time per sample without really changing the water activity value. And then one more example. So this makes up a lot of our customer base, which is looking at meat snacks. So if you've got sausage sticks, cured meats, beef jerky. Again, now we're dealing with muscle tissue, so that damage to the sample really starts to play a big factor in our final water activity. So in looking at this, ideally what you want to do is try and keep whole intact pieces of that product, especially if you're dealing with whole muscle meat snacks. There was a good report out there. If anyone has questions at the end about that, I'd be happy to share that with you, that actually looked at preparation methods. It was done outside of here, and they found that for whole muscle meat snacks, the intact samples gave better and more consistent results. So we've seen the exact same thing, taking whole pieces. If you're pulling large pieces off the line, what you actually should do is, just take some scissors or something and cut that into pieces to fit in the cup. The center example here, just chopped up, that works really well, especially if you've got varying thicknesses, just to get a little bit more representation in your sample. Again, what you want to avoid is what we see on the far right, which is a finely ground or shredded meat snack. If you're selling a piece of jerky, you're not selling ground meat, so you're actually altering that sample and getting different water activity values, and again, you're introducing variability into those readings by having something that will change with the environment more readily. And then one last thing on sample preparation is looking at how to optimize this yourself. So in a lot of these examples, I've showed you maybe 3 different ways to prep the sample. For your own process, you could basically do something like on this screen here. Take your product, look at how it reads with no sample preparation. Do like a single cut or slice to expose the interior. Take a reading on that, and then grind the sample either with a mortar and pestle or a food processor, whatever you have available. And what you want to look at is the comparison of what the water activity value is across those 3 preparation methods, and then the read time as well. So something like a cookie or an antacid tablet, pretty homogeneous mixture in a lot of cases. So the sample preparation method really doesn't matter. You don't see a significant impact on the water activity values, regardless of how you prepare it. In some cases, you might see a difference in read time, which is great. Something like a gel-coated solid dosage form, however, if you look at the no sample preparation reading of 0.458 versus 1 cut or slice or ground, you can see both of those values are much lower, and that's simply because if you read it whole, we're reading the surface or the exterior. Once you expose the interior, then that's actually a contributing factor to the water activity reading, so you do see a difference. So for your own optimization, take a bunch of different samples, prepare them in a couple different ways, and just take readings on each of those prep methods and look at read time and value, and you can kind of tweak what's going to work best for your process. So in conclusion, the 4 things that we really talked about as being key contributing factors to getting fast and accurate results, kind of the insider strategies here, are making sure that you're monitoring and controlling temperature, as that's a key variable for water activity. You want to reduce sample exposure, which is going to give you more accurate and repeatable results as well, and making sure that you're preserving those samples appropriately. I went over some special sample types that require some special prep methods or considerations. And then lastly, hopefully I've given you some ideas going forward on some sample preparation methods and kind of the best way to approach sample preparation for your own product.